Hi, my name is Thomas Nestmeyer and I'm excited to tell you about our work on learning physics-guided phase relighting under directional light. Relighting describes the process of transforming an input image taken under a given input light direction, shown on the left, into a target image with a new target light direction, shown on the right. As a teaser, you can see our result in the middle. Recent works achieve impressive relighting results but are all limited to smooth lighting. When relighting from one directional light to another, they do not perform well. For example, the methods single image portrait relighting and deep portrait relighting both fail to show realistic relighting effects such as cast shadows. Our method, employing a directional light representation, does not require assumptions of smooth lighting, but still allows us to generalize to arbitrarily complex output lighting. Our architecture is best visualized in two stages. Stage 1 infers the two intrinsic components albedo and normals from the input image. Given a target light direction, we can then compute shading from the normals and multiply with the albedo estimate to obtain a diffuse relighting. In stage 2, we use all stage 1 modalities to predict a non-diffuse residual and a light visibility term for cast shadows. Composing them with the diffuse relighting from stage 1 according to our structure decomposition produces the final relighting. Back-to-back execution of both stages results in a fully differentiable end-to-end architecture. The final relit result is guided by an adversarial loss similar to pix-to-pix. Each intrinsic prediction is guided by an individual loss for which we chose the structured dissimilarity measure after thorough evaluation. To collect the necessary data, we built a light stage and captured 21 subjects with different head poses and facial expressions. This results in a total of 482 captures split into training, validation and test set by subject. Each capture is lit consecutively with 32 directional lights and recorded with 6 calibrated cameras. One such capture, taking roughly half a second, can be seen on the right. The intrinsic components needed for guidance are then extracted using photometric stereo. We applied several data augmentation techniques to fully leverage the available data. Here we show the intrinsic components of our architecture inferred by our method in the upper row, while the lower row shows the corresponding ground truth signal or closest capture. From the input image, we predict in stage 1 albedo and normals, which are rendered into the target shading and combined with the albedo into a Lambertian relighting. We feed these modalities into stage 2, where we predict the shadow mask and residual, here decomposed in terms of its sign, for the final relit result. Because light is additive, we can easily perform image-based relighting. In the environment map seen on the upper left, we sample multiple light directions and sum up the relit results with their corresponding color. Here we show our result for a test subject under multiple rotating environment maps, both for typical facial expressions as well as expressions uncommon during training. The final composited results simulate realistic relightings. This clearly demonstrates that the assumption of a single target light direction is not a limitation, but a benefit of our work. We further demonstrate relighting of subjects occluding their faces with hands, subjects assuming non-frontal head poses, and a test subject with dark skin color, all relit with the same environment map. To show its general applicability, we took spontaneous photos with a consumer camera in a regular office. This environment exhibits multiple light sources and ambient light. Although this is against our model assumptions, our method handles these cases gracefully. We show multiple such relighting results to demonstrate that the model assumptions of a single source light direction are also no actual limitation. We illustrate the benefits of our method in a comparison to related work. First, SFSNet, both pre-trained as provided by the authors and retrained on our dataset for fairer comparison. Inherent to this model is its diffuse reconstruction, which looks flat under directional light, as can be seen when comparing to the closest ground truth capture. The second work shown here, pix-to-pix, has no structural constraints and can therefore predict specularities and cast shadows. However, its lack of intrinsic guidance often leads to physically inconsistent results. Our result on the lower right consistently outperforms these methods. In summary, we present a physics-guided relighting approach utilizing a structured decomposition into intrinsic components. Our method produces realistic relighting from a single face portrait with effects caused by strong directional lighting such as specular highlights and hard cast shadows. For more information, please visit our project page. Thank you for your attention.